Hello, kiddos, and welcome to our podcast on intermolecular forces. So, for this podcast, we're going to take a look at the forces that happen between molecules, not inside the molecules. So, for today's class, we're going to look at the different types of intermolecular forces, such as London dispersion or London force, dipole-dipole attractions, and hydrogen bonding. We're going to relate the properties of substances to the predicted intermolecular bonding in the substance. Pretty much what I'm going to do is we're going to learn about what each of these are, and then we're going to be able to look at a substance and predict what type of forces are in that substance. So let's take a look at the background. Just a little bit of background information for you. All chemical changes are accompanied by energy changes, right? So remember, chemical changes, you're forming a new product. Basically, energy is seen as mostly light, heat, or electrical energy. Energy can be released slowly, such as in a battery. It's a chemical change that actually creates electricity in a battery, or quickly, such as fireworks. Two types of energy changes are possible. Now, these look familiar to you, right? Exothermic and endothermic, of course. But let's take a look at it from a chemical point of view. So you know that exothermic is the energy that is released into the surroundings. So it actually, if you were touching something that was going through an exothermic reaction rather, it would feel hot, as opposed to an endothermic reaction where energy is absorbed from the surroundings. So if you were touching something that was undergoing an endothermic reaction, it would feel cool to the touch, not because it's actually cold, it's because it's removing the heat, or it's using the heat, or it's absorbing the heat from your hand. But let's take a look at it from a chemistry point of view. In an endothermic reaction, the product's bonds have less energy than the reactant bonds. As compared to an endothermic reaction, the product's bonds have more energy than the reactant bonds. So what is bond energy, kiddos? Bond energy is the energy required to either break a chemical bond, so you require energy to break a bond, or the release when a bond is formed. So when bonds are being formed, heat is being released or energy is being released. When bonds are being broken, or when they have to break, energy is required for that, which makes sense, right? There are three types of forces in matter. This is a little FYI. You're not going to be tested on this, but the previous slide about what exothermic and endothermic reactions are and how they relate to bond energy, that might be a question on an assessment. Intranuclear force. Intra meaning inside, nuclear meaning in the nucleus, and that's the bond that exists between the protons and the neutrons. That bond is very, very strong, kiddos, or that force is very, very strong, because you never ever see protons and neutrons leaving the nucleus. The nucleus always stays intact, and it's very, very strong. Intramolecular forces, those we've learned already. Intra meaning inside a molecule. So bonds between atoms within the molecule, or between ions within the crystal lattice. So these are intramolecular forces. They're either found in a molecular substance, like water, for example. It'd be the bond between the hydrogen and the oxygen in water, or between ions in a crystal lattice, which is the strongest ionic, well, not the strongest in the world, but out of the three, it's pretty strong. Basically, it's the bond that exists in, for example, a crystal lattice of sodium chloride. Intermolecular forces is what we're going to learn today. Now, notice that it's inter, it's not intra. Inter is between. So the bonds between molecules, all of these are weak. There's only three you have to memorize, but they're all weak. Keep in mind they're weak compared to these guys, but they're still really important in life, okay? They're electrostatic, which means we're dealing with poles, or we're dealing with a positive end and a negative end. Sometimes these positive ends and the negative ends are permanent. Sometimes they're just there for a quick second. Here's an example. This right here, inside the molecule itself of water, these are intramolecular forces. This bond here that bonds a positive end of one molecule to a negative end of another molecule, for example, that's where these intermolecular forces come from. So there are three types of intermolecular forces. You do have to memorize all three, and you do have to know what makes them unique. And then you do have to be able to look at a molecule and say, hey, this has this force, it doesn't have this force, and then you have to back it up with data. Okay, you are going to have a written response question on your final for your unit, and you do have to back it up. And it's easy to back it up, so don't even worry about it. So there's dipole forces, London force, also known as London dispersion force or dispersion force, and finally hydrogen bonding. Keep in mind all these three types of intermolecular bonds are far weaker than anything else. These are much stronger. However, they're still consistent. They're still influential on how matter behaves. Now, out of those three, the strongest is hydrogen bonding, and the weakest is London force. Dipole fall somewhere in between the three for strongest. So what is dipole? I'll actually go back and talk a little bit about this. If you see this word, van der Waals force, okay, don't be alarmed. It just includes, it's the combo of London force and dipole forces. Okay, so let's talk about dipole force first. It's a simultaneous attraction between oppositely charged ends of polar molecules. Simply put, it's the attraction between dipoles. Okay, let's take a look at this example. Hydrogen has an EN number of 2.2. Chlorine has an EN number of 3.2. Obviously, 3.2 is higher than 2.2. You're going to have a dipole. Because this is not going to change, these EN numbers are not going to change, this dipole is permanent. It's always going to be there. And you guys remember what happens when at the pointy end of the arrow, that shows that these electrons are being shared closer to the chlorine. Because the EN number is higher, there's a stronger pull. So we give that a delta negative, and obviously the other side has a delta positive because it lost an electron. Not fully, it's not transferred, but it's being scooched over to the chlorine side. That is a permanent dipole. So when I have two of these together, as you can see from the diagram, okay, this right here is dipole-dipole. It's a force or a bond between a negative end of one molecule to the positive end of an adjacent molecule. And you might have another one here. It might look like this, where you still have an attraction between the positive end and the negative end. So let's take a look at the definition. Quite simply, the dipole definition is a partial separation. So basically we're talking about that there's a negative end and a positive end, right? Of positive and negative charges within a molecule due to electron negativity differences. And these are permanent dipoles. So dipole-dipole lands somewhere in the middle in terms of strength. Dipole-dipole forces are among the weakest intermolecular forces, but still control important properties, such as solubility, okay? Because water is polar. So remember, like dissolves like. Only polar molecules will be dissolved in water. Molecules that are nonpolar, they will not dissolve in water because water is polar. So here's just another kind of deeper thinking about dipole-dipole force. In a liquid, for example, polar molecules can move and rotate to maximize attractions and minimize repulsions. The net effect is a greater overall attraction. So basically what that's saying, substances like water that are polar, they will rotate and move around, so the positive end is mostly attracted to the negative end. Positive and negative attract. They try to move around so there's fewer repulsions and more attractions. And that's why water has things like surface tension. Okay, it's because of these attractions. The strength of the dipole-dipole force is dependent on the overall polarity. So the more polar a substance is, the higher the dipole-dipole. Okay, moving on. In a liquid and in a solid, dipole-dipole forces in a solid, okay, like all ionic substances, all ionic substances are solid at room temperature, and they all form these cool things called crystal lattices, okay? And what happens here is this positive and negative, there's an attraction between the positive and negative. In liquids, the attraction isn't as strong because they're constantly moving, right? So it's still an attraction between the positive and negative, it's just not as strong. What is a London force? A London force is a simultaneous attraction between a momentary dipole. Now it's not a permanent dipole, it's a momentary dipole, and they actually last for a fraction of a second. And the momentary dipoles in surrounding molecules. So let's break that down. What does it mean? How does that look? What does that look like? Well, let's take a look at the definition first. Momentary dipole, an uneven distribution. So it's an uneven distribution of electrons around a molecule resulting in a temporary charge. So we have a temporary charge, so it's not a permanent dipole, but it does exist for a fraction of a second between its ends. So let's take a look at that. Let's take a look at lithium. So lithium has 3 electrons. We can all agree that lithium has 3 electrons, and we can also agree that at some point, and remember, electrons are constantly moving. They're constantly moving. So it's very probable that these electrons go from having an even distribution to an uneven distribution. So as you can see here, all of a sudden, for a fraction of a second, there's more electrons on one side than the other. When that happens, you get this momentary dipole. Okay, it only lasts for a fraction of a second, and what that does is it causes the other, an adjacent lithium molecule, right? Here's the nucleus. Because this is the negative side, it pushes the electrons away to the other side, causing another momentary dipole. So this happens with every single substance. Every single substance has London dispersion because every single substance has electrons. Another thing to keep in mind is that the more electrons a substance has, and that's total electrons, kiddos, not just valence electrons. That's very, very important. The more electrons a substance has, the higher the London force. Because if you have lots and lots of electrons, the probability of having an uneven distribution increases. So Fritz London also showed that momentary dipoles occurring in adjacent molecules would result in an overall attraction. So here we have an uneven distribution of lithium. This is now a negative side, right? Because negatives, negative plus a negative repel, the electrons of an adjacent molecule are going to be whisked away somewhere else, causing another momentary dipole. The strength of the London force is directly related. So directly related means as one goes up, the other thing goes up, to the number of electrons in the molecule. And that's total electrons. Total electrons. Not valence electrons, total electrons. And inversely related to the distance. That makes sense. Inversely related means opposite. The farther away a molecule is from its another molecule, the lower the probability of having London dispersion. Okie dokie. So increase in electrons is equal to increase in force, which is directly related, and an increase in distance is equal to a decrease in force. That's an inverse relationship. Okay, let's continue on. The key point is that the more electrons a molecule has, the more easily momentary dipoles will form. So this is the higher probability. The greater the effect of the London force will be. So obviously, it has a higher London force if it has a higher amount of electrons. So if that were a question on a test, kiddos, you can't just say, oh, this molecule has higher electrons. I want data. I want you to actually count the total number of electrons and be like, yeah, I'm proving to you I know what I'm talking about. This substance has, let's say, 50 electrons, whereas the opposing substance only has 20. London forces are present in all molecules, whether any other type of attraction is present. What that means is no matter what, every substance has London dispersion. So why do we care? We use our understanding of dipole and London force to predict boiling points, also hydrogen bonding, but we'll talk about that later. So let's compare some substances. Let's start with this substance here, CH4. It has 10 electrons. Let's compare that to SNH4. It has 54 electrons. Well, this guy is going to have a higher boiling point than this guy. And these are all negatives, kiddos. So obviously, negative 52 is a higher number than negative 164. These are all gases. So gases typically have very low boiling points, right, because they're gases. So all this is proving is that the higher the total amount of electrons, the more the London dispersion. There's no other forces. There's no dipole, because this is nonpolar, 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 nonpolar. One central atom, the 4 peripheral atoms are exactly the same, so it's going to be nonpolar. A higher boiling point temperature means more energy has to be added, thus we assume the intermolecular forces are stronger. That's logical. If I need more energy to break bonds, clearly that means that the forces are higher. Remember, if all other factors are equal, the more polar the molecule, the stronger the dipole-dipole force, and if you increase the number of electrons, it increases the strength of the London force. Both of these have an impact on boiling points. Let's look at an example. Use intermolecular force theory to predict which of the following hydrocarbons has the highest boiling point. Well, let's compare methane, ethane, propane, and butane. Okay? Only one carbon, 2 carbons, 3 carbons, 4 carbons, 10 hydrogens on the last one, 8, 6, and 4. So what you're going to do is you're going to ask yourself, are the molecules polar or nonpolar? Okay, they're nonpolar. So if they're nonpolar, there's no dipole-dipole. That comes off the table. Which has more electrons? Butane has the greatest number of electrons because it has more carbons and more hydrogens. Therefore, it has the greatest London force. So let's check to make sure. Here's butane. It has the London force, boiling point, of negative 0.5 as compared to methane, which is negative 162. This has a way higher boiling point, and that's only because it has a greater London force. And the reason it has a greater London force is because it simply has more total number of electrons. Let's take a look at example number 2. Use intermolecular force theory to predict which of the following has the highest boiling point. Okay, let's take a look. Bromine or iodine monochloride? Well, which has more electrons? Okay, what do? They're called isoelectronic, which means they have the same number of electrons. This has 70 electrons. This guy has 70 electrons. And that's total electrons, remember, not valence electrons. Do not make that mistake. Okay, so problem. Both have the same number of electrons. So what do we have to do? We have to figure out which is polar, which is nonpolar. Bromine, because it's the same, right? If it's the same, it's going to have the same En number, 3.0, 3.0. The electrons are going to be shared equally, so it's nonpolar. Okay, let's take a look at iodine monochloride, ICl. Iodine 2.7, chlorine 3.2. There's a difference, so those electrons are going to be shared closer to the chlorine. This is polar. So if it's polar, it has dipole-dipole, right? This has no dipole-dipole because it's nonpolar. Bromine is nonpolar, has no dipole-dipole force, only London force. Iodine monochloride is polar, has dipole-dipole force, and it also has London force. Keep in mind, this is important because they have the same number of electrons, so the London dispersion force is the same. Let's check. Okay, both have the same number of electrons. This is nonpolar. Oh my gosh, my writing, so sorry. And polar, higher boiling point than bromine. You cannot predict boiling points when, I won't do this for you guys, one molecule has a stronger dipole-dipole force and the other has a stronger London force, because how can you even explain to me why one is going to be higher than the other when it's all over the place? So I won't give you this example. The two molecules differ significantly in shape. Now, we're not going to get into this in Chem 20, but it's a thing in Chem 30. Shape also has to do with boiling points. Okay, so I'm not even going to go into that in Chem 20. Just know I won't give you that kind of question. I'm not going to give you a question where the central atom of either molecule has an incomplete octet. That would be rude. Okay, here's some practice if you want it. Moving on, hydrogen bonding occurs when a hydrogen atom is bonded to a strongly electron-negative atom. It only happens, now it happens a lot, but for you, for all of us, we're only going to look at the hydrogen bonding when hydrogen is bonded to nitrogen, oxygen, and fluorine. Those have a significant difference. All the other ones, oxygen, all the other things that are bonded to hydrogen, even though it's a thing, it's not enough of a thing. So for us, we're only going to be concerned with hydrogen bonded to a nitrogen, oxygen, and fluorine. That's it. That's all. You do have to memorize those three. Here's an example. Water. This hydrogen, okay, which has is the positive end of a polar molecule, is attracted to this oxygen because it's oxygen, right? This right here is hydrogen bonding. Hydrogen nucleus proton is simultaneously attracted to the two pairs of electrons, one closer in the same molecule and one further away on the next molecule. So basically, what that means is, let me erase this and show you. There's an attraction here, which is intramolecular, and there's an attraction here, intermolecular, inside the molecule, between the molecules. Why do we need a strongly electron negative atom? It pulls the hydrogen's electron away, making it unshielded, so the lone pair on the other side can come much closer. And there has to be this bond here between the hydrogen and the oxygen in order to have this bond here between the adjacent hydrogen and oxygen. Let's continue with hydrogen bonding. Hydrogen bonds are momentary attractive forces between passing mobile molecules, but are the strongest. So these are not permanent, but they're the strongest out of the three. But they're still all weak compared to intramolecular forces. Hydrogen bonds only act as continuous bonds between molecules and solids, where the molecules are moving slowly enough to be locked into position. Okay, water has hydrogen bonding. It only becomes permanent when it's frozen. So when it's ice, it's the hydrogen bonds that make ice a solid, because these hydrogen bonds, remember, as you lower the temperature of things, movement starts to decrease. As the movement decreases because of lower temperatures, those bonds become locked in. They become locked in. Hydrogen force would have been a better name because it's still just a force. Okay, let's talk about ice. In ice, hydrogen bonds form between the molecules, and what happens is you get this rectangular hexagonal crystal lattice shape. Now, what's cool about this shape, kiddos? It has 1, 2, 3, 4, 5, 6 sides. Okay, that's why we get snowflakes. It's because of hydrogen bonding. Another cool thing about hydrogen bonding, the most part of this is actually open space. So that's why water is the only substance that as it cools down, as it freezes, okay, it actually becomes less dense, and that's why ice floats. The hydrogen bond represents a hydrogen nucleus proton being shared unequally between two pairs of electrons. Basically, you have inter, intra, inter, intra, inter, intra. Do lakes freeze from the bottom up or the top down? Top down, just talked about it, because water is unique in that its solid form, ice, is less dense than its liquid form. Why? Because hydrogen bonds hold water molecule in a hexagonal lattice with open space in the center, which explains the low density. Now, that's not by accident. God knew what he was doing. He's like, man, I can't have things freezing from the bottom up. All the fish will always die. So it's top up. You still have room for the fish to move around and life to continue existing. It's a pretty smart dude, that God. Another cool thing is that between the DNA structure, it's hydrogen bonding, right? The double helix of the DNA molecule owes its unique structure largely to hydrogen bonding. The red bonds are hydrogen bonds. If the helix were held together by covalent bonds, the DNA molecule would not be able to unravel and replicate, and guess what, kiddos? Life could not continue. So another cool fact about hydrogen bonding, helps things replicate, because this is going to break apart, it's going to replicate, and it's going to make human life possible. Why do we care about intermolecular forces? It explains things like surface tension, the shape of a meniscus, and capillary action. There's some surface tension examples. Basically, I'm not testing you on this, is just some FYI. Molecules within a liquid are attracted by other molecules in all directions equally, but right at the surface, molecules are only attracted downwards and sideways. This means that the net pull is downwards so that the surface tends to stay intact. The stronger the intermolecular force, the stronger the surface tension. And that's why we get droplets of water. Okay, this shows water adhering to the faucet, gaining mass until it's stretched to a point where the surface tension can no longer bind to the faucet. It then separates and surface tension forms, and it drops into a sphere. Capillary action due to adhesion and cohesion. Adhesion is attraction between unlike molecules, and cohesion. Like molecules, water is attracted to water in cohesion. Water is attracted to the substance where it's beside, that's adhesion. Between water and glass is greater than the cohesion between water molecules, and you get this thing called the meniscus. And remember, in science, you always measure to the bottom of the meniscus. And capillary action also helps with things like thermometers. And that's about it. Okay, hope you enjoyed that. Just continue with the practice at the end of the notes, and we will see you again with our last podcast. Have a good day.